Hi everyone, in this video tutorial we will learn how to repair a cracked rectangular plate with composite material in Abaqus. First, we will learn how to model a crack in a rectangular plate and get the energy G integral in contours of the crack. After that, we will learn how to model a composite plate patch repair for our cracked plate and compare between two cases with and without patch. Let's get started. Let's start with creating of our parts and make necessary partitions in the part. Let's go to create part, solid plate, 3D deformable, solid extrusion, continue, and let's create sketch and add dimensions to our sketch with 100 millimeter in the width and 200 millimeter in the height or length of our plate, and we will use 2D 2 millimeter in the thicknesses of our plate. As you can see here, we have our plate, and now the necessary steps is to create partitions to represent the crack and necessary partitions to simplify the mesh of our plate. Let's create partition using sketch. Let's create sketch in the face, and now the first line is the line represent the crack with the length equal to 10 millimeter. Line is the first and necessary partitions in our plate to represent the crack. The second line is for simplify the mesh in the mesh step, and also we will sketch more lines in our parts to create partitions to simplify the mesh. Now the another step is to create circle in the front of the crack to make the mesh specific in this circle or in this face to evaluate the G integral or stress intensity factor. Click done. Now we have necessary partition in the face, but we need the partition in the part, the wall part. In this step, we will create partition in our part using the sketch in the face. Let's go to partition cell, extrude sweep edge, and select the first partition. We need to partition the part into two cells using these edges. Click OK and select along direction, extrude direction. Click OK and create partition. Now we have two partitions in our part. The first one, second one, with the same tool. Select the cell and click on select edges to create partition. Click on extrude along direction. Select direction. Click OK and create partition. Now we have two partitions in this cell. Let's do the same step. Select cell, click on, select edge to create partition, select on, extrude along direction, select direction, click OK, and create partition. Now we have partitions in this cell. Let's do the same step in this cell also. Click done, select edge, select extrude edge, create partition. In this cell also, click done, select edge, select extrude edge, create partition. In this cell, we need to create partition in this into two parts, into cells. Let's remove this one, delete, yes, and make partition using these edges first. First one, second, let's select one, select edge, extrude edge, create partition. Now we have this cell, this, and in the last one, click on, select edge, along direction, click OK, create partition. Now we have necessary partitions in our parts. Now let's go to create material and assign the material to our part. We will use elastic behavior for steel material. Let's go to mechanical elasticity elastic and add Young modulus and strength ratio. The Young modulus is in the megapascal units. Okay, and let's create section. Continue material. Okay, and now let's assign our section to our part and click OK. Select section. Okay, now we have assigned our section to our part. Now let's go to the next step, the assembly step, and create instance, apply. Okay, now let's go to the step and create analysis step. We will use static analysis. Okay. In the next steps, we will go to find output and history output, but for now we will go to interaction and create our crack in our part. Let's go to special inertia or special crack and create a sine seam. This step will create the crack and select the the space when we need to use the crack. For example, in our case, we have in this zone we will use and create the crack and click OK. The selection, we have an error. The selected instance is independent instance. Let's go to assembly and convert to make independent. Select make independent and let's go again to special crack, assign seam, and select the zone where we need to create the crack. Select this zone and click OK. As you can see here, that seems like we have no material in this face, in this zone. That means we have no material. Click OK. And now let's create the crack in the same zone. Let's create crack 1, contour integral, continue, and for now let's select the crack front, the first contour. we will select this edge, the crack front, click OK, and also select normal to crack and select the direction of our crack. Now we have this tab for our crack. We have the type, the name, the domain, general information about the direction of our crack, and also let's use go to singularity, and we can change the value of mid-set node. You can use 0.25 and use collapse with single node or duplicate nodes. Click OK. Now let's return to the step again and go to history output, edit, and in the set select the crack. Let's select crack and select crack 1. For the crack, for this crack, we will get the G integral or CT integral or T stress or stress and toxicity factor. Let's select G integral and also select the number of contours for our calculation. And for example, in our case, we will use 4 contours and click OK. Now, let's go to interaction again. And we will create the interaction and create reference point to apply our load. Let's go to tool, create reference point, select reference point, and also let's create coupling, continue between, let's select constraint control, the control point, click on, select the surface to control, and click done. Now we have constraint coupling created, click OK. Now let's create boundary condition in our part. First boundary condition is the constraint in the initial step. Click done, select the bottom face, the bottom face of our part, click on cluster, OK. Now we will apply boundary condition in the reference point created before. Let's select displacement rotation, click OK, select reference point, click done, and in this case we will select all displacement in all direction, just the displacement in the y direction. And now we can apply the displacement in the step 1 in this boundary condition and apply 50 millimeter displacement in the y direction. Click OK. As you can see here, that this is the direction of our displacement. Now let's go to the mesh step, add mesh our part, select assign mesh control, select the crack front zone and select hexadominate, sweep medial axis, click OK, select mesh by edge, click on and select by number. Let's mesh this zone. Okay. we have problem in mesh. Let's mesh the wall part. Click yes. As you can see here, we have the mesh around our crack. Now let's go to assign element type and see the element mesh type. We have standard 3D stress. You can use quadratic, and we have C3D D8 reduced integration. Click OK. Click done. Now let's go to the next step. The last step we will do in this modeling is to set the reference point or set this point to get the displacement and force, reaction force in our model. Let's go again to step and create history output, create a new one, continue, select set. Let's go to create set before, the tool set, create, force, select geometry, select this reference point when we apply the boundary condition and apply displacement. Click done. Now let's go to create a new history output, select set and select the displacement and the reaction force in the y direction. To get the result of our simulation in the and get the reaction force displacement curve. Now let's go to mesh again and we will minimize the size of mesh in our model. Select 5. Okay, and mesh our parts. Let's use one. This is the cross mesh. Apply, delete previous mesh. Okay, mesh, click yes. Now you can use less than the size of our mesh in these zones because we don't need this zone in our mesh. In our result, let's use 2 millimeter in the size of elements. Click mesh yes, and now for the first result we will use this mesh size. Let's go to the job and create the job and run simulation. View. Okay, and submit our job. We have completed job. Let's go to the result and see our data of simulation. The first, let's plot the deformed shape. As you can see here, we have the opening crack. Let's also plot the contour stress in the front of the crack. Let's go to hide unnecessary edges using these two, and we have this result and shape of our opening of crack. Let's go to get the result and plot the data of the force displacement curve. Let's go to ODB history output. And as you can see here, we have these data, the coordinates, and also the G integral value in each contour. We have 5 contours, and also we have the force displacement. Let's plot the force displacement curve first. As you can see here, we have the force displacement. Let's go to combine and operate on X with Y data. Continue, select combine, displacement, force, plot expression. Now, as you can see here, we have the force displacement. We have 50 millimeter in the displacement. Need this value of our force in the Newton to get this displacement. That this displacement need 3 times 10 power 6 Newton to get as a reaction force. Let's add another viewport. And this is our result of our simulation. But let's go to the job again. Go to monitor. And in data file, we will go to the estimated G integral contours in each contour. We have the correct name. And we have the value of G integral in each contour. In the second part of this tutorial, we will create repair patch for repairing our cracked rectangular plate and make comparison between two configuration with and without crack, with and without patch. Let's get started to create the, the patch. Create part. For example, let's add a name patch. 3D deformable solid extrusion. Continue. And let's create a rectangle, and let's add dimensions to our rectangle to represent our patch. For example, 50 millimeter in the height and 50 millimeter in the width, and also add thicknesses to our patch with 1 millimeter. Click OK. Now we have our patch dimensions and geometry. Go to create assembly to add our patch to our cracked rectangular plate. Now let's translate this patch to the right position in the crack. Select this point and translate to this point. Now we have the right position of our patch around our cracked plate. As you can see here, we have our patch with our cracked plate. Now let's go to create composite material property and behavior. Create material composite mechanical elasticity elastic. In this step, we will use lamina type as type of our elastic material, and let's add young modulus or composite material in all direction. This is the property of our composite lamina type. Click OK. Now let's assign create composite layer, add a name batch, and also use the initial play count. For example, we will use 10 layers in our batch. Click continue, and now this tab appear in our interface. The first step is select the region of our material of our layer. Click done. We have an error because we select shell element. Let's ignore this step and try again. Composite layer batch. Select continuum shell rather than conventional shell because we have solid part. We need to use continuum shell. Click continue. Select region and select solid part. Select material. Select composite material, and also we will select the thicknesses of each layer. For example, in our case, we will use 0.1. You can use more than these thicknesses in each layer depending to your configuration. And let's also rotational angle, rotation angle. Let's use for our case, we will use 0 degrees, and integration point we can use 1. Click OK. Now let's click OK. Now we have assigned our layers composite to our batch. Let's go to query, play, please stock plot, and select cell. As you can see here, we have 10 layers with orientation equal to 0. You can edit your configuration in composite batch. You can change angles depending to your configuration. Another side, we will use the layer orientation, the main option, the main step in our modelization is this step is configuration the orientation of layer depending to your parts. The first, we have these options. Let's select, let's return. Let's go to parts global. You can use select the orientation global with global system of our patch. Now, as you can see here, the the first orientation is with the x direction. The x-axis is the first orientation, and the second orientation of layer is with the y direction, and also the third direction is with z direction. In our case, we have simple and no, no complex shape. That's enough for our orientation. But if you have complex shape as pipe or any others, need more configuration of system of orientation of layers. That this option is sample for our case, but if you have complex shape, you need more configuration and use more steps to make right configuration and right orientation of layers in the composite part. For now, let's go to step interaction and create interaction between the badge and rectangular cracked plate. Let's use find contact pair tool and find contact pairs in our model, in the wall model. As you can see here, we have one contact in the contact between the badge and cracked plate interaction. Let's select die to add die interaction between the badge and rectangular plate. Click OK. Let's go to interaction manager, or you can go there, and as you can see here, we have constraints created between the badge and cracked plate. With die type, that means we have the perfect interaction and the perfect contact and perfect translation of and transfer of load and stresses between two instances. Now let's go to the mesh and mesh our composite batch with element size equal to 2. Apply. OK. Mesh our part. Click yes. As you can see here, we have all necessary mesh in our instances and assembly. Now let's go to the job and create job. New. OK, and submit. Now we have completed job. Let's go to the result and let's remove mesh edges, and you can see the result of our simulation. Let's create a new viewport and open the previous job, previous result, to compare between the two results. Compare von Mises stresses after repair our rectangular plate. Let's go to Nick 2 viewport, and as you can see here, you can see the von Mises stresses around the crack is decreased in the repaired sheet. Another side, let's go to the job again and go to monitor, go to data file, and also you can get the result of G integral contour and compare the result in 5 contours and compare between the first job. Until now, I hope you enjoyed with this video. Don't forget to subscribe in my YouTube channel and like this video. See you.